Hello, my name is Zaid Al-Jindi, and this presentation serves as the Abu Dhabi University URIC submission about a quantum convolutional neural network architectural block for object detection. So as time goes by and more complex AI models are developed to meet increasingly demanding requests, a problem comes with how costly these models become to train. To exemplify this, the Olofy 11 median model contains 68 billion floating point operations per second. It's known that the environmental and ecological implications of these models are significant, with hundreds of billions of liters of water used just to cool their data centers. An alternative to complex computing tasks is with quantum algorithms like the Deutsch-Jozsa algorithm that has a complexity of O of 1 compared to its classical counterpart's exponential complexity. This is because of the quantum property of superposition, whereby multiple candidate states can be considered simultaneously in one unit of work, which omits the need to perform multiple sequential operations classically to achieve the same goal. Previous literature in quantum machine learning, specifically computer vision, is somewhat limited, however, mostly focusing on binary classification problems with few dedicated for object detection and visual transformers. Furthermore, most binary classification QML problems use the same approach of reducing a circuit down to one qubit, which when measured provides the class prediction. A block like Yolovi 11 spatial pyramid pooling fast focuses on more than simple classification, improving a sub-capability of the model, which is its scale invariance or ability to detect objects from various distances. Therefore, the project proposed is to combine quantum computing principles into object detection by proposing a quantum SPPF block or the QSPPF block. The original SPPF block contains two convolution layers and three max pooling layers. To construct the QSPPF block, ansatz, which are parametrized quantum circuits, will be used in place of the convolutions, whilst der Hoyer's algorithm can be used as the max finding algorithm in the max pooling layers. So I'll start by explaining quantum computing basics. Qubits can be thought of as vectors that live inside of a three-dimensional sphere called the block sphere. The z-axis of the block sphere determines what state a qubit can be in. If a qubit's vector points closer to the 0 state, it will measure 0 once observed. And if it is closer to the 1 state at the bottom, it will measure 1 once observed. To change the probabilities of measuring 0 or 1 and a vector's position, quantum gates are used in a circuit. The other axes refer to a qubit's phase, which affect how a qubit might react to certain gates. The ansatz design consists of rotational gates that rotate a qubit about the y-axis, and entangling gates which turn a state into an unfactorable one. This works to increase the expressivity of a search space. The RY gates use variable weights to decide how much to rotate the qubit's vectors by. As the original block uses one-by-one convolutions, the ansatz is designed to process channels of the same pixel 16 at a time to be exact. RY gates can also be used to encode multiple channel values into the qubits by rotating them before the ansatz is applied. To get an output feature map, expectation values can be measured, which are normalized values that represent the average outcome across a large number of measurements. In this case, the number of encoded channels per qubit is equal to the number of expectation values per qubit. As in the original SPPF block, the number of input channels must equal the number of output channels. Der Hoyer is an algorithm based on Grover's algorithm, which works by iteratively shifting the solution state's vector closer to a deterministic measurement, while decreasing the chance of measurement for non-candidate solutions in each diffusion operator. Quantum circuit complexity can refer to its depth, which measures the number of sequential layers assuming parallel execution across qubits. We can process Cmax channels per each qubit, assuming one channel per qubit, where Cmax is the largest power of 2 less than the number of available qubits. If we repeat this Cn divided by Cmax times, we can process height times width pixels. This gives a complexity of O of height times width times Cn divided by Cmax. However, you can also encode multiple channel values per qubit, which can allow you to be able to process all channel values in one ansatz application, giving a complexity of O of height time width. In terms of max pooling, since the de Hoyer complexity is O of root of n, then the pooling complexity will be O of height time width times Cn time p, where p is the pooling size, as opposed to the classical complexity of O of height time width times Cn time p squared. For the actual implementation, Der Hoyer was tested to work, but was too resource intensive, which would have caused training to take multiple weeks if a quantum simulator was used. It also sometimes gave slightly inaccurate results. Instead of the tested approach using two quantum convolutions and quantum max pooling, the approach only used two quantum convolutions and classical max pooling. Testing was conducted on several variants of the QSPBF model, including a 2-qubit ansatz one with 8 channels encoded per qubit, a 4-qubit one with 4 channels per qubit, and an 8-qubit one with 2 channels per qubit. All models performed relatively similarly to the classical model. However, the 4-qubit ansatz model outperformed in every regard save for recall. This came at a cost, however, which is training time. Quantum computer simulators have to generate and keep track of every possible state in a superposition. For a large amount of qubits like 8, that means keeping track of 2 to the power 8 states. This, however, wouldn't be a problem if real quantum hardware was used, as superpositions wouldn't need to be simulated. The 2-qubit ansatz and 4-qubit ansatz models resulted in training times of approximately 15 hours, whilst the 8-qubit ansatz model needed close to 20. Efforts were made to reduce this, such as implementing multi-threading, where each thread was in charge of processing its own 16-channel partition, multiprocessing, where a separate process was started for each partition, and multi-batch, which utilized Qiskit's own multiprocessing and its estimator for expectation values. Due to the GI lock of Python, the multi-threaded and multiprocessing approaches resulted in slower times, with the multi-batch approach offering the fastest processing time. As for all metrics, all models' results graphs followed very similar trajectories. The Pearson correlation of all models' trajectories to the classical models was actually measured in the high 90s. It also revealed some interesting characteristics, like how the 2-qubit ansatz model dropped farther than the others in box and DFL loss. However, this trend is inconsistent with multiple training trials that were performed. The models were trained on the African wildlife dataset, which featured images of different African animals. In terms of classification, all models ranked highest in classifying rhinos above all classes. However, interestingly enough, the 2-qubit ansatz model had the highest precision out of any class by any model at 0.899 for the rhino class. The overall mean average precision, though, with an IOU of 0.5 still is credited to the 4-qubit ansatz model, with a mean average precision of 0.837. In keeping with the promise of lower parameters, the total parameter count was also compared between the quantum and classical models. All quantum models saw a reduction of approximately 160,000 parameters to the classical model. In terms of visual differences, both models present with stronger and weaker detection and classification ability in comparison. The 4-qubit ansatz model, for example, was able to more correctly classify a rhino in 3208.jpg with a higher confidence, whilst the classical YOLO V11 model misclassified the head as a separate detected rhino. The 4-qubit ansatz model was also able to detect and classify a buffalo correctly in 1136.jpg compared to the classical YOLO V11 model that detected and classified it as a zebra. However, in 4283.jpg, the 4-qubit ansatz model misclassified 2 zebras as rhinos, whilst the classical YOLO V11 model correctly classified them as zebras. There are multiple common areas of strength, such as the multiple correct classifications of buffalo with confidence scores of 0.9 to 1 across both models. Both models also share common weaker capabilities shown in 1177.jpg, where several trees were classified as zebras by the classical YOLO V11 model, whilst the 4QA model only classified one tree as a zebra. To conclude, the favorite approach was in using the 4-qubit ansatz model over a classical model for all performance metrics. However, the results cannot be fully classified as conclusive since the weights were randomly initialized in each run. To get a better overall reading on effects, the next step would be to pre-train the ansatz weights like the rest of the YOLO weights. To also get a better reading, real quantum hardware can be used, which can solve the issue of impractical training times and allow for the inclusion of quantum max pooling. However, more efficient algorithms like one called CUMSA could be used to avoid problems caused by de Hoyer and inaccuracies. If all the above objectives can be met, then quantum influence can be expanded to include the entire YOLO V11 pipeline rather than this one block. Thank you.